Good afternoon. Our Team Telecom guys would like to present our final project, Compressive Sensing Decoder. Next slide, please. Here you can see the outline of our talk, and we would like to start with the problem relevance. Existing wireless networks are designed with the goal of increasing the spectral efficiency in order to serve human needs. Next generation of wireless networks will face a new challenge in the form of massive machine-type communication, where a huge number of autonomous devices connected to one access points. One of the perspective schemes for dealing with this problem is default ALOHA. In this scheme, active users transmit their data without any prior communication with the base station. The main idea that we have to decode the noisy sum in time slots. And in our project, we consider a compressed sensing decoder. Next slide, please. So now we can go to the system model. We have k active users and v time slots. Each user encodes the binary message into a code word of length n and apply binary phase shift gain modulation. So after modulation, our code word will belong to the alphabet ±1. Next slide. Thus, in slot, we receive the sum of t messages and want to determine each one. We can represent the sum as a multiplication of matrix A and sparse vector B plus Z. That it is additive white Gaussian noise. Here we consider matrix A is a metric with all possible modulated code words as columns, B is activity vectors with exactly tail ones, and other zeros. Next slide. Consequently, our decoding task can be reduced to searching the right activity vector. So it should be arg minimum of such vectors with t1s. If we consider the second norm, this is non-negative least square problems or bounded variable least square problems. If we consider the first norm, it is compressed sensing problem. If we apply coord decomposition, we can find our B via pseudo-inverse matrix. Next slide. So how we generated our codebook? Firstly, we generate all possible binary vectors of length k. These are our information vectors. Then we encode them with LTPC code to generate a matrix. So each information word of length 10 was encoded to a code word of length 35. And after that, we modulate it and achieve sensing matrix A. Next slide. So now we can go to the problem solution. Firstly, we tried non-negative least square problems where the coefficients aren't allowed to become negative. So this is problems in the term of a second norm. Also, we decided to improve this approach. We searched not t maximum, but some number, for example, 10. Then we consider all possible combinations and find the minimum distance in terms of the second norm.
Another method that we considered was bounded variable least squared. Here we investigated two approaches. The first one was with the use of SciPy library least squares function that solves a nonlinear least squares problem. And another one with LSQ linear function that is designed for solving a linear least squares problem with bounds on the variables. So both methods are designed for minimizing residual second norm square with constraints on vector x. Next slide, please. Here you can see the efficiency comparison of BVLS and NLS methods. We plotted error probability with respect to signal to noise ratio. Here you can see that BVLS and NLS methods for our modified approach, where n least equals to 10, were more efficient than other approaches. Next slide, please. Another method that could be used in our problem is QR decomposition. So we estimate the solution of a linear system with the use of it. And as our matrix is not square, here we need to compute a pseudo inverse of it. Next slide, please. In this slide, we compared all of our methods. and here nonlinear squares with bounds and bound terrible squares looked more efficient than other methods. Next slide, please. Also, we compared chaotic compositions with an NLS for different values of t. As you can see, these methods were most efficient when t was equal to 2, with chaotic composition and less competing this value of t. Next slide, please. Also, we measured mean execution time for our methods. Least square with bounds was the slowest one, as it is designed for nonlinear problem solution. The fastest one was chaotic composition, as it is not an iterative algorithm and involves only one matrix computation. Next one, please.
So we can also take under consideration another approach to construct sensing matrix A. Suppose that we know that codewords in the channel are from some set of size m, where m is significantly less than 2 to power k, where n, in this case, we obtain matrix with shape n, and where n is length of codeword, and m instead of 2 to power k. Such matrix has other properties, and for matrices with relation m to n approximately equal to 2, we can use compressed sensing, a method for signal recovery. For such matrices, we obtain good enough results. How we implement compressed sensing? It's non-trivial task, and so we use discrete Fourier transform. The main idea of compressed sensing is to find such solution that minimize L1 norm, not L2. We apply discrete cosine transform to sensing matrix and then use lasso linear model to minimize L1 norm. Lasso finds such coefficients and then we apply to them inverse transform. Indices for greatest absolute values correspond to the most probable transmitted codeword. In this slide, there is comparison of compressed sensing and previously discussed methods. For two different cases of sensing matrix A, when m equals to 60 and to 120. It can be seen that compressed sensing show results comparable to the best algorithm, in this case QUAR, when number of signals per channel T is equal to 2. And when matrix shape is 3560. But when we have more than 2 signals, the best results, and it can be seen earlier, can be obtained with algorithm NNLS. For greater shape, 35120 compressed sensing show worse results. And if we look at time comparison for matrix shape 3560, the fastest methods are NNLS, QUAR decomposition, and compressed sensing, while BVLS and least squares with bounds show worse results. That brings me to the conclusion. Summing up, we have considered problem of recovering a few signals in one channel with Gaussian noise. In original article, only non-negative least squares were used. First, we suggest some improvement using additional minimizing for the signals over L2 norm. We have tried different approaches such as compressed sensing and QUAR decomposition and different variants of bounded least squares. We have provided a comparison for different number of signals per channel for different T, and we also provide the comparison for time execution. The best performance show p-values in case of big matrix, but when we have a number of signals per channel more than 2 and some other construction of sensor matrix, optimal algorithm can be COR or an NLS. Thank you for your attention. If you have any questions, we will be happy to answer them.